Welcome to section 3.4, solving exponential and logarithmic equations. Now that we have learned about logarithm properties, the product, quotient, and power properties, we're going to use those and the one-to-one properties and inverse properties to be able to solve either exponential or logarithmic equations. We're going to start with exponential first. We're going to solve and round to the nearest thousandth, so 3 places. So 4 raised to the x is equal to 32. First off, there are different ways to solve these. As long as you're using those properties, you can really solve them in any way you want. So the first one I'm going to show you, 4 raised to the x is equal to 32. If you recognize that the base for 4 and 32 can be rewritten as a common base, we can rewrite 4 as 2 squared. And we can rewrite 32 as 2 to the 5th. So therefore, 2 raised to the 2x, it's a power to a power, so you multiply. And then 2 raised to the 5th, we can now use the one-to-one property since the bases are the same, and say that 2x is equal to 5 divided by 2, and x is equal to 5 halves. So 4 raised to the 5 halves is equal to 32. Alright, there's other ways to solve that, but that one right there we're going to do as the same base and use the one-to-one property. On example B, e raised to the x is equal to 45. Now on this one we can't find a common base, so we're going to use the inverse properties. Right now it's written exponentially. Okay, so it's base e. Well, if we're using base e, then that's our natural log. So we're going to rewrite this using the inverse property. We're going to write the natural log on both sides. Natural log of e raised to the x is equal to natural log of 45. And that actually what we're using is the one-to-one property because we're rewriting it as a logarithm on both sides. Now, what is natural log of e? This is where the inverse property comes into play. So this is the one-to-one property, but then the next one we're using is the inverse because natural log of e, that cancels out, and that's x is equal to whatever the natural log of 45 is, and when you plug that in, you get 3.807 rounded to the nearest thousandth. Okay, so that we use the one-to-one property to set it up, and then we use the inverse to cancel the natural log of e. And once again, natural log is log base e of e raised to the x, and that's why they cancel out. They're inverses of each other. On C, when we're solving exponential and there's other stuff with it, we have to isolate it just like we do a lot of our other equations and functions. So we divide by 4. 3 raised to the x power is equal to 10. Once again, we can't find that common base. So on this one, we are going to use log, and we can pick any base we want. So since it's base 3, we're going to choose log base 3 of x and log base 3 of 10. So once again, using the one-to-one property right there. And then now because of inverses, we can cancel log base 3 of 3. So that is x is equal to log base 3 of 10, which you can use the change of base formula, log of 10 divided by log of 3, so x is approximately 2.096. Alright, let's continue with a couple more here. You might want to pause and then try to do as many as you can, then come back. But these are definitely a little bit more challenging than what we just did. So in example 2a, once again we want to isolate what is there, so we're going to add the 3 to the other side. And then you have 4 times 2 raised to the 3t minus 7 is equal to 18. And then you'll divide everything by 4. So we get 2 raised to the 3t minus 7 is equal to 18 fourths, which reduces to 9 halves. So we have base 2. So we're going to rewrite this as log base 2 of 2. And so this is log base 2 of 9 halves. So once again, this is written using one-to-one, and then we're going to use the inverse to cancel log base 2 of 2. So that's 3t minus 7 is equal to log base 2 of 9 halves, or 4.5. We'll add 7 and divide by 3. So t would be equal to log base 2 of 4.5 plus 7, and then all of that is divided by 3. So t is approximately, on this one, 3.057. So on example 2 here, 2b, we got two bases, cannot rewrite 2 and 5 as a common base, but you also have two exponents with the variable. So let's see how this is going to work out. Instead of picking base 2 or 5, we're just going to do base 10. So we'll rewrite it as log base 10 of 2 raised to the x and log base 10 of 5 raised to the 2x minus 5. And so we can use the power property to move the exponent to the front of both of these. So this would be 2x minus 1 times log of 5. We'll then distribute, not on the first one is just multiplication, x log of 2, and then we'll distribute log base 5 to the 2x minus 1. So that'll be 2x times log of 5 minus log of 5. And so we have two x's here. We're going to subtract the 2x log 5 to the other side. And since we're not able to combine these, we will factor, use the distributive property, take that x out, and then that will leave us with x times the quantity log 2 minus 2 log 5 is equal to negative log 5. And now we can divide both sides by log 2 minus 2 log of 5. So when you plug that into your calculator, make sure you have negative log of 5 divided by, and the denominator needs to be in parentheses. And plug all that in at one time, and you will get x is approximately 0.637. Alright, example 2c. E raised to the 2x minus 4, e raised to the x minus 5 is equal to 0. On this one, it's set up as a trinomial that we could potentially factor, but I want you to recognize that e raised to the 2x can be rewritten as e raised to the x raised to the 2. And the reason I'm doing that is so that you can see when you go to try to factor this one what your terms are going to be. So e raised to the x would be ex, e raised to the x minus 5, and then e raised to the x plus 1. And so if you multiply that out, ex, e raised to the x, times e raised to the x, you add your exponents. So x plus x would be 2x. And so that's why that works out that way. And so now you can say e raised to the x minus 5 is equal to 0. E raised to the x plus 1 is equal to 0. So e raised to the x is equal to 5. E raised to the x is equal to negative 1. And then you can rewrite this as the natural log of e raised to the x and the natural log of 5. Those cancel, that's your inverse. And so x is equal to natural log of 5. And then on this one, that would be natural log of e raised to the x is equal to natural log of negative 1. And you might recognize that right here, you'll notice that the natural log of negative 1, that value is not greater than 0. And since that value is not greater than 0, the natural log of negative 1 will not work. So we only have one answer here, and that is the natural log of 5. And the natural log of 5 is approximately 1.609. And then this one doesn't even work. So this is your only answer on this equation. Now we're going to look at some logarithm equations. And once again, this section is all about solving, so we're just looking at a lot of different possibilities, a lot of different examples that you could see. So on this one, once again, we're solving round to the nearest thousandth. This is the natural log of x is equal to negative 3. I don't mind you writing log base e of x if that helps you recognize that natural log has base e. So log base e of x, how are we going to solve this? Well, we want to use our inverse property here. So if you have log base e of x is equal to negative 3, we can rewrite this as e raised to log base e of x, or natural log of x, is equal to e raised to the negative 3. So we are using the one-to-one property, whereas before we were writing them as logarithms. Now we're writing it exponentially. So e raised to the natural log. Why? Because this then cancels out based on your inverse properties. So x is equal to e to the negative 3 raised to the negative 3. So x is approximately equal to 0.050 0. And the reason the 0.050 is because you get 0.0497 on your calculator. And so when you go to round, this needs to round up. And since it's a 9, that 49 rounds up to a 50 then. All right, let's take a look at the next one. Now, the first one, natural log of x, was already isolated. This one, we're going to have to subtract the 4 and then divide by 3. So 3 natural log of x is equal to 8. And then divide by 3, and we get the natural log of x is equal to 8/3. And so once again, in terms of solving it, we're going to rewrite this as e raised to the natural log of x is equal to e raised to the 8/3. That will cancel, so x is equal to e raised to the 8/3. Plug that into your calculator and you get x is equal to approximately 14.392. Example 3c, 2 log base 5 of 3x is equal to 4. Once again, we need to isolate the logarithm, so this will be log base 5 of 3x is equal to 2. We'll rewrite this one using the one-to-one property of 5 raised to log base 5 of 3x. And once again, the reason we choose base 5 is because the logarithm has base 5. So they cancel out because of your inverse property. 3 of x is equal to 5 squared, which will be 25. Divide by 3, and you get 25/3. So if we round that to the nearest thousandth, that'll be 8 and 1/3, so 8.333. And so there's once again just a couple more examples of solving some logarithms. We'll look at a couple more on the next slide. Example 4, we got solve round to the nearest thousandth again. So on the first one, you got log base 8 of 92 equals x. That's really just a change of base formula that we learned the other day. So therefore, x is going to be approximately equal to natural log of 92 divided by natural log of 8. Not to confuse you, you can pick any base here. We can do log base 10 of 92 divided by log base 10 of 8. And then when you plug that into your calculator, you'll get x is approximately 2.175. All right, on B, couple options here. One, if you recognize, you can actually move the natural log of 7 to the other side. And by doing that, it actually creates an easier equation on this one, because now you can use the one-to-one property, and since you have a natural log of x equal to the natural log of 7, therefore x will be equal to 7. Okay? If you didn't recognize that, you could actually use your quotient property. Since it is subtraction, we could rewrite this as the natural log of x divided by 7 is equal to 0. And then to get rid of the natural log, we would do e raised to the natural log and e raised to the 0. So those would cancel on the left and get x divided by 7 is equal to 1, because e to the 0 is 1, times it by 7, and x is equal to 7. So there's different ways that you could look at that one. On 4c, we have 3 logarithms. First off, logarithms do not cancel. You have to use the one-to-one properties or the inverse properties. So on the left-hand side, it is being subtracted log base 2, and there's no numbers in front of log base 2, so we don't have to use the power property. We can go straight to the quotient. Log base 2 of x minus 5 divided by 6, that's the quotient property, is equal to log base 2 of 3. Now we can use the one-to-one property with a logarithm of base 2 on both sides. Therefore, x minus 5 divided by 6 is equal to 3. Once again, the logarithms are not canceling. It's a one-to-one property that we're using. Now you can multiply by 6 and then add 5. And so if you do that, you get x is equal to 23. All right, and the last example I'm going to show you today on the notes is 2 natural log of x is equal to natural log of 2x minus 3 plus natural log of the quantity x plus 2. So if you have a number in front of a logarithm, you need to use the power property so that you can use the one-to-one and inverse property. So we're going to rewrite this as the natural log of x squared is equal to, then we're going to use the product property to create one logarithm on the right-hand side. So we'll do the natural log of, and I'll go ahead and multiply these two together. So that'd be 2x squared plus 4x minus 3x, so that's plus x, and then minus 6. Now you have the natural log equal to a natural log, so we can use the one-to-one property. So we use the product, and then we also use the power on that one, and then we're going to use the one-to-one. So this is x squared is equal to 2x squared plus x minus 6. You see the quadratic, so we want to set it equal to 0. You subtract the x squared, and we are left with x squared plus x minus 6 is equal to 0. We can then factor x plus 3, x minus 2. Set factors equal to 0. And we get x is equal to negative 3, and x is equal to 2. Now, one thing that I haven't mentioned as I went through all these different problems is we should actually be checking them with the logarithms, because remember that when you have log base a of x, x must be greater than 0. So on this one, you have natural log of x, so that must be greater than 0. You have natural log of 2x minus 3, that must be greater than 0, which means x must be greater than 3/2. And you also have x plus 2 must be greater than 0, which means x must be greater than negative 2. So that represents your domain as to what those values must be. Now, if it's greater than 0, all right, that has to occur, which means this x equals negative 3. When you go to plug that in for there, right, for that x value, it's not greater than 0. So therefore, x equals negative 3 is out. If you plug the 2 in, that's fine. If you plug the 2 in for 2x minus 3, that would give you a positive 1. And if you plug the 2 in for the other x, you would get a positive 4. And you can also see x is equal to 2 is greater than 3/2, it's greater than 0, and it's greater than negative 2. So our only answer on this one is x is equal to 2. Now, let's go back and just double check our logarithms to make sure that we didn't have any others as we went through. So x is equal to 23. If you plug 23 back in for x, 23 minus 5 is 18. So that works. On b, if you plug x equals 7 in, that's positive, that's good. And then on a, that wasn't the value we were looking for, so the 2 point, that was the exponent, so the 2.175 is okay. And then on these, it's 3 times x, so 3 times a positive 8.3 repeating is positive. This x, it could be positive 14 something, that's fine. And then once again, this x can be positive as well, or should be positive, and it is. So we didn't make any other mistakes on the other ones, but we need to make sure that when we get those answers that we are checking to make sure that that domain value must be greater than 0 there when you plug it back in. And so now take a moment to write down your summary for this lesson.